Okay, welcome to Quantum Godsec screencast. Today we will be building random number generator that is based on principles of quantum mechanics instead of simple pseudo random number generation. So after this screencast, your brain will be bigger, will be smart. So that's really good. Okay, quick reminder on bits. Bits can be either in 0 or 1 state. There is nothing in between. So usually the bit 0 can be represented as simple 0, but what we can do is also represent it as an array. So we have this simple binary state, meaning that our array can have one either on index 0 or on index 1. It's simple and I hope intuitive. If not, read up on it. And then we can quickly move to qubits. So we will be working with Cirq library. If you don't know how to install it, Google it. It's simple. Sooner or later, as any sort of person working with software, you need the super skill of Googling stuff. And yeah, if you are too lazy to do it, then you can stop watching probably. Okay, so what we will do is first talk a little bit about qubits and then start actually using qubits, so using Cirq. Okay, so yeah, let's do it. So qubit can also be represented as an array. That's really great. And it can also have the same states, but what is important is that it can also be anything in between. So this is what is sometimes well, it is called superposition, but it is sometimes referred in popular media as this, that the qubit can be in multiple states at the same time, which is not really true. It is simplification that sounds really magical, and you can have all sorts of quantum leaps, quantum this and quantum that. So yeah, let's get to it. Basically, what qubit is a simplest system that have the all intricacies of quantum mechanics. But what do I mean when I say that the state of the qubit can be anything in between? So we can have, for example, 1.5, 0.5 here and 0.5 here. But what we need to do, actually, let's call it qubit row. It needs to be normalized to always be a vector of length 1. We will import numpy. Okay. Beautiful array. I wonder whether it will work like that. And we will okay, that's fun. So as you can see, the actual qubit has the value and position 0 equal to 0.707 and so on, and the same in the position 1. This is because it is actually 1 over squared square root of 2. So this happens only because it gets normalized to a vector of length 1. Because if you recall, this is not a vector of length 1. Qubit row actually will have length of square root of 2. 1 over square root of 2. This is why we need to divide by this value. Okay, so every qubit needs to, if we want to represent it as an array, it needs to have a length of 1. This comes directly from principles of quantum mechanics. You can read on it. And here we will not focus on physical reasons. We have more of quote unquote hacker approach, meaning we are interested in what we can actually build with it, what we can hack away with it, how it works, and get some fluency with the Cirq library. Okay. So knowing that, we can start having fun with Cirq itself. So what we will do is build a very simple circuit. You will create qubit. That is called Apollonia because it's a beautiful name. If you ever have a daughter, you should name her Apollonia. Okay. Or a boy, I don't judge. Okay, so as you can see, the Apollonia qubit is named Apollonia. Nothing special happens. What we need to do is actually build a circuit and then run a simulation. Okay, so how we can build a circuit. We can use the circuit class, and there are basically two ways. Either we call circuit constructor directly, with the elements of the circuit. Okay, or we can append the elements of the circuit. Sorry. Okay, that's, I would say, quite simple. Now we have simulator, and of course we need to create an instance of simulator. So what we did, we create a named qubit, meaning that when we visualize the simulation, the qubit will have name Apollonia. We can refer to it in various results as Apollonia. We then created circuit. We appended a gate that measures the state of the qubit and returns result. Because, as I did not say before, the qubit itself will be in this weird state of 1, for example, in 1 over square root 2 in 0 state and 1 over square root of 2 of 1 state, having probability 50-50 to measure, and that's the critical part, in either state 0 or 1, because the qubit before measurement is actually in the superposition, meaning that we are not sure what the actual state will occur during measurement. But when we measure actually the qubit, we collapse it into a regular classical bit state, so it is either 0 or 1. So the measuring process basically collapses our qubit into one of two possible states. But if we measure it multiple times, it turns out that the probability is exactly as the state of the qubit that we, funnily enough, cannot know directly, but due to operating on the qubits, we can clearly show in what state it is just before measurement, meaning what probabilities the qubit will return. Okay, so I hope that will become clear by the end of the video. So we have our circuit. We can print it to see actually how it looks like. Okay, so we have Apollonia qubit. There's a quantum wire, and then a measurement gate. Simulation has not been run as of now. So let's see what happens now if we run the simulation. Simulate circuit, and this will be a result. Okay, and what we can print the whole results for starters. Okay, so this is this weird notation called Dirac notation or cat or bracket notation. But what we've got as a result is actually a qubit in state 0. The measurement of Apollonia is 0. And when we will run it multiple times, it will always remain 0 because right now the state of our qubit is purely bit 0. So this means that the bit is in purely 0 state, or qubit is purely in 0 state. There's no probability in for it to be in state 1. Okay, and this weird notation, it means that because qubit actually is a can be represented, state of the qubit can be represented as a state vector in space of complex numbers, then we have this part, the real part, the imaginary part. But what we always need to remember that this vector needs to be normalized to a vector of length 1, and then this first part is value squared would be probability of it being in state 0, and this squared would be the probability of it being state 1. Okay, so this is why we had here 1 over squared root of 2, because it squared gives us the 50% probability of the qubit to be in state 0 and 50% of it being in probability state 1. Okay, so now we've got the basics. You are smart, you understand it. Even if I'm rambling, that's all fine. So what we will do right now is try to build a quantum random number generator. To do that, because whenever we create a qubit in a Cirq, it will be always in state 0. But what we need to do is prepare such a circuit that it will move it to this state 1 over square root to 1 over square root 2. And then by actual law of physics, we will have 50% of it being in state 0 and 50% of it being in state 1. So that's as random as it can get. It is randomness guaranteed by actually law of physics, by actual law of physics, and that's fun. Okay, so what we will need in here is some transformation of the state from from 0 state to this 50-50 state. And every gate or every transformation of qubit can be thought as a basically combination of the state multiplied by a matrix. This matrix is not completely arbitrary. It needs to be a unitary operator, if I recall correctly. And one of those gates, you can actually do it with pen and paper of what this matrix needs to look like for it to translate it from this state into 1 over square root of 2 and 1 over square root of 2. But the gate, pro tip, the gate is called Hadamard gate. It takes us from one measurement basis to another, but that does not matter yet. It basically transforms 0 vector into this 50-50 probability vector. There's a lot more of depth into what actually Hadamard gate does and actual states, but we will dive into it way later. Now we are just building stuff and having fun. Okay, so the Hadamard gate is also called an H gate. Not very original, but easy to remember. So we will append to a circuit. And now, before even running simulation, we will see how the circuit looks right now. First, we want to use the Hadamard gate, and then we will measure. Don't be a dum-dum like me. Okay, so we have Hadamard gate, and then we can measure it. And what we can do right now is use a very nice feature of the Cirq, which is step-by-step circuit walkthrough, which is probably not possible with physical realization. But hey, we are using simulator, not actual quantum computer, and it is a great learning tool. Simulate moment steps of our circuit, and we will print the following. So we will number the step. We are interested in this. And we are interested in the state. The state can be called by state vector. I think that's it. The method. Yeah, there are some implementations, so we'll see whether it works. Okay. That's really great. So what you can see in here is that at the step 0, of course, we have the proper indexing starting with 0. So after applying the H gate, we have need a comma here. We have state 1 over square root of 2 and 1 over square root of 2 in either of 0, 1 states. And then the actual measurement, when I ran it previously, it was in 0 and now it is in 1. So as you can see, it is relatively random, if we can call it that. Okay, So that's a simple way of generating random numbers in Cirq. And those numbers, of course, this is simulator, but with actual quantum computer, this this qubits this qubit, beautiful qubit called Apollonia, would be returning actual uh, random distribution of 0 and 1, or actual random bits of 0 and 1. Okay, so let's now pack it properly into something that we can reuse in future. Fun, fun, fun. So our goal, we will build a class called quantum random number generator. And we will need to generate a binary array of some length, and it will return numpy array. Okay. And this is because in future screencasts we will reuse this class to actually generate random numbers. And in here we will generate binary array of any length that we will provide. So first we need to create qubits. We want to give them some proper naming. And this range method gives us ability to create multiple qubits at once with some prefix to name. The prefix will be QRNG as from quantum number generator. Okay, so we want to apply the Hadamard gate to every qubit. Okay, because we want to change the state of the qubit from this 1, 0 to 1 over square root 2 and 1 over square root 2. We want to create a measurement gate. And we can measure all of the qubits at once instead of measuring one by one. It basically is more convenient for our application. We will call it QRNG measure. Now we can build the circuit. So it will consist of H gates and measurement gate. And okay, the result will have a simulator in here, simulate the QRNG circuit, and we can measurements return the result of the measurement, and this will work exactly as intended. Of course, let's do some proper housekeeping. So probably the simulator should not be created every single time we call this method, and if we will need to pass some specific properties to the simulator instantiated with some specific state, it makes more sense to pass it as a constructor argument. And if the simulator is none, then maybe for convenience we will create a new instance, but in general, self simulator is the argument that we pass. So in here, we can use the simulator passed as an argument. I am no Python developer, but we will have a constant in here called measure gate name, and also the qubit name prefix. Okay, that's probably how we need to call it. Okay, that's fun. I hope it works as intended. So what we will do now is the same file for the sake of it. Just create a QRNG. Without the simulator, that's the instance created, and we can create a binary array of this length, and let's see whether it works. So now we created this array, the second time another array. Okay, we can also print the circuit to see how exactly it does look. Okay, I don't Okay, so as you can see, every qubit is turned into a different state by the well, in the same actual state by Hadamard gate, and then we measure them all at once, and we've got this beautiful array as a result. We can also print okay. As you can see, the measurement was 0111, and the qubits were individual qubits were in state 0111. And this way you can tell your parents that you mastered the law of quantum mechanics, and you can and you created the actual quantum random number generation using simulation. And yeah, thank you very much for your time. Leave your comments. I'm just learning, just as you. So yeah, hopeful to have a lot of more those screencasts and where we can approach the quantum mechanics in a more, however we want to call it, but a way that makes me enjoy recording those screencasts.